Hello. I'm going to go through the OCR 2023 AS Level, Chemistry, Paper 1, Breadth in Chemistry. If you find this video useful, please click like, and leave a comment, as it will help me to carry on making more videos like this. In the fixed comment under the video, I leave a link to my website jctnotes.com where you can see the written answers to this paper. We start with section A. The first question asks which statement explains the trend in boiling points down the halogens group. A. Covalent bonds become stronger. B. Induced dipole-dipole interactions, London forces, become stronger. C. Ionic bonds become stronger. And D. Permanent dipole-dipole interactions become stronger. The halogens exist as diatomic molecules, and their boiling points increase as we move down the group. This trend is primarily due to induced dipole-dipole interactions, London forces. These are weak intermolecular forces that arise from temporary fluctuations in electron density within molecules or atoms. As we progress down the halogen group, the size of the halogen molecules increases because they have more electrons and larger atomic radii. Larger molecules possess more electrons, which enhances the polarizability of the electron cloud. Consequently, the electron cloud can be more easily distorted, resulting in stronger temporary dipoles. Stronger temporary dipoles lead to stronger induced dipole-dipole interactions. Thus, as we move down the group, London forces become more substantial, requiring more energy to overcome these forces, and leading to higher boiling points. Option A is incorrect because the boiling points of halogens are not determined by the strength of the covalent bonds within the diatomic molecules. They are influenced by the strength of the intermolecular forces between the molecules. Option C is incorrect because halogens do not form ionic bonds in their diatomic molecular forms. Option D is incorrect because halogen molecules are nonpolar and they do not exhibit permanent dipole-dipole interactions. Therefore, the correct answer is B. In question 2, we have a hydrocarbon containing 85.71% carbon by mass. We are asked what is the empirical formula of the hydrocarbon from the four given. To calculate the empirical formula, I always create a table with 5 columns. The first column is for the name of the atom. The second column is for the atomic mass. The third column is for the mass of percentage of each atom. In the fourth column I calculate the number of moles by dividing the mass with the atomic mass. In the last column, I divided each number obtained in the previous column by the lowest number obtained in the previous column. The first column and third columns are filled with the data of the problem. As it is a hydrocarbon, the components are carbon and hydrogen, with an atomic masses of 12 and 1 respectively. We are given the percentage of the carbon as 85.71%. We can find that the percentage of hydrogen is 100 minus 85.71 equals to 14.29. If we divide the percentage by the atomic masses, we get 7.14 for the carbon and 14.29 for the hydrogen. The lowest value is 7.14, therefore we divide each number of moles for 7.14 and we get 1 for the carbon and 2 for the hydrogen. Then, the empirical formula is CH2 and the answer is B. In question 3, we have the reaction of methane with steam of water to produce hydrogen and carbon dioxide. We are asked what is the atom economy of the hydrogen in the process. The atom economy is defined as the mass of the desired product divided by the mass of all reactants multiplied by 100. We start with the reactants. The mass of methane is 1 times 12 plus 4 times 1 equals to 16 grams. We have 2 moles of water, each mole provides 18 grams, then, the water provides 36 grams. Therefore, the mass of all reactants is 36 plus 16 equals to 52 grams. As desired products, we have 4 moles of hydrogen. As each mole has a mass of 2 grams, the total mass is 8 grams. Then, the atom economy is 8 divided by 52 and multiplied by 100 equals to 15.4%, and the answer is C. In question 4, we are asked the number of p orbitals occupied by electrons in sulfur atoms, 2, 4, 6, or 10. The sulfur has the orbitals 1s, 2s, 2p, and 3s fully occupied. There are 4 electrons to fill 3 orbitals 3p. As the electrons occupy any free orbital before they pair, 2 orbitals will have 1 electron and the third orbital will have 2, instead of having 2 orbitals with 2 electrons each. Counting the number of p orbitals with electrons, we have 6, consequently the answer is C. In question 5, we are asked which substance has the lowest oxidation number for sulfur: sodium sulfate, natural sulfur or sulfurate, sulfur difluoride and sulfur dioxide. If we take a quick look, we'll see that in S8, the oxidation number of sulfur is 0 because this is its natural elemental form. In the other compounds, sulfur will have positive oxidation numbers since oxygen and fluorine are more electronegative and tend to pull electrons away from sulfur. So, S8 has the lowest oxidation number for sulfur and the answer is B. For completeness, let's check the oxidation states in the other compounds, though you wouldn't need to do this exam since showing your work doesn't score points in this part. I leave a link on the description where I explain in more detail how to find oxidation states. Sodium sulfate. We have 2 sodium, each sodium has a contribution of +1, then, the total contribution is 2 times 1 equals to 2. We have 4 oxygen, each oxygen has a contribution of -2, then, the total contribution is 4 times -4 equals to -8. Sodium and oxygen have a total contribution of 2 - 8 equals to -6. As the compound is neutral, the -6 charge is compensated by 1 atom of sulfur, and its oxidation state is +6. In the sulfur difluoride, we have 2 fluorine, each with an oxidation state -1, therefore, the total contribution is 2 times -1 equals to -2. As the compound is neutral, the -2 charge is compensated by 1 atom of sulfur, and its oxidation state is +2. In the sulfur dioxide, we have 2 oxygen, each with an oxidation state -2, then, the total contribution is -2 times 2 equals to -4. As the compound is neutral, the -4 charge is compensated by 1 atom of sulfur, and its oxidation state is +4. In question 6, we are given successive ionization energies of an element in period 3 of the periodic table. We are asked to identify the formula of the oxide of the period 3 element from a list of 4 provided. The ionization energy is the amount of energy needed to remove the most loosely bound electron from an isolated gaseous atom, positive ion, or molecule. More than the absolute values of the ionization of energy, we are interested in the biggest difference between successive values. This big jump occurs when we start removing electrons from a more stable, inner shell rather than the outermost shell. For this example, you can see that the biggest jump is between the third and fourth ionization energies, with a value close to 9,000. The other jumps don't even reach 5,000. Since the biggest jump is between the third and fourth ionization energies, it tells us that a considerable amount of energy is needed to remove the fourth electron, so the ion formed will be X3+. From the oxide compounds given in the answer, we can identify it as aluminium oxide, Al2O3, and the answer is C. In question 7, we are asked how many oxygen atoms are in 120.2 grams of silicon dioxide. The molecular mass of the silicon dioxide is 1 times 28.1 plus 2 times 16 equals to 60.1 grams per mole. Dividing the 120.2 grams by the molecular mass, we obtain 2 moles of silicon dioxide. As each mole of silicon dioxide has 2 moles of oxygen, we have 4 moles of oxygen. That multiplied by the Avogadro number, give us 2.408 by 10 to the power of 24. Rounded to 2 decimal places, we get 2.41 by 10 to the power of 24 atoms of oxygen. Therefore, the answer is C. In question 8, we are given the reaction of decomposition of magnesium nitrate when heated. It produces magnesium oxide, solid, and 2 gases, nitrogen dioxide and oxygen. We are asked to calculate the volume of gas produced at room temperature and pressure when 0.0025 moles of magnesium nitrate decomposed. Looking at the equation, we can identify that the only gases involved are the nitrogen dioxide and the oxygen. The other 2 species are solid. From the stoichiometry of the reaction, each mole of magnesium nitrate is going to produce 2.5 mole of gas from the 2 mole of nitrogen dioxide and half mole of oxygen. This means that 0.0025 moles of magnesium nitrate is going to produce 0.00625 mole of gas. At room temperature and pressure, a mole of an ideal gas occupies 24 cubic decimeters. Then, 0.00625 moles of gas will occupy 150 cubic centimeters. The answer is D. In question 9, we have the reaction between zinc and aqueous silver nitrate to produce silver metal and zinc nitrate. We are asked what is the mass of silver metal formed when 0.10 grams of zinc is added to 15 cubic centimeters of 0.25 mole per cubic decimeter aqueous silver nitrate. We start by calculating whether the limiting reactant is the zinc or the silver nitrate. Using the atomic mass of zinc as 65.4 grams per mole, we can find that 0.1 grams of zinc is 0.00153 mole of zinc. We can also calculate that 15 cubic centimeters of 0.25 molar of silver nitrate is 0.00375 mole of silver nitrate. The stoichiometry of the reaction indicates that we need 2 moles of silver nitrate for each mole of zinc. This means that 0.00153 mole of zinc requires 0.00153 times 2 equals to 0.00306 mole silver nitrate. As we have 0.00375 mole of silver nitrate, more than 0.00306 required by the zinc, the silver nitrate is in excess and the limiting reactant is the zinc. From the stoichiometry of the reaction, we have that 1 mole of zinc produces 2 mole of silver, therefore, 0.00153 mole of zinc produces 0.00306 mole of silver. Using the atomic mass of silver as 107.9 grams per mole, we get 0.330 grams of silver. The answer is C. In question 10, we have that 15 cubic centimeters of 18 mole per cubic decimeter concentrated hydrochloric acid is diluted with water to prepare 250 cubic centimeters of dilute hydrochloric acid. We are asked what the concentration is, in mole per cubic decimeter, of the dilute hydrochloric acid. We can use that the product of the initial concentration and volume is equals to the final concentration and volume. Replacing the values that we have, we get that the concentration is 1.08. Then, the answer is D. In question 11, we are given the statement that the standard enthalpy change of formation of water is minus 286 kilojoules per mole. Which statement or equation from the 4 given is correct? The standard enthalpy change of formation is defined as the enthalpy change when 1 mole of a compound is formed from its elements in their standard states under standard conditions. From the statement, we have that in the case of water, the reaction is 1 mole of hydrogen gas plus half mole of oxygen gas to give 1 mole of water liquid, and the value is equals to -286 kilojoules per mole. Option A gives the equation of the enthalpy change of formation of water. However, the value of the enthalpy is incorrect. A is not a valid option. Option B refers to 2 moles of water and the value of the enthalpy should be double than the value stated. This option is also incorrect. Option C refers to bond enthalpy. Bond enthalpy is the amount of energy required to break 1 mole of a particular type of bond in a gaseous molecule. Bond enthalpies are always positive because breaking a bond requires energy. As the value given is negative, we can discard option C. Option D refers to the standard enthalpy change of combustion of hydrogen. The standard enthalpy change of combustion is defined as the enthalpy change when 1 mole of a substance is completely burned in oxygen under standard conditions. In the case of the hydrogen, the equation is 1 mole of hydrogen gas plus half mole of oxygen gas to give 1 mole of water liquid. This is the same equation than the standard enthalpy change of formation of water, and, therefore, its value is -286 kilojoules per mole. This statement is correct and the answer is D. In question 12, we need to find which statement about energy changes is correct. Option A says, combustion of an alkane is endothermic. Combustion of an alkane is a reaction between oxygen and the alkane to produce water and carbon dioxide, or carbon monoxide, depending on the conditions. This reaction releases energy, this means, it is exothermic. Then, option A is incorrect. Option B says, in an exothermic reaction, more energy is needed to break bonds than is given out when bonds are made. The energy balance of a reaction can be calculated as the difference between all the bonds broken and all the bonds made. In an exothermic reaction, the total energy is negative. This means that the energy to break bonds is lower than the energy to made bonds. Therefore, this statement is incorrect. Option C says, the activation energy is a negative value. The activation energy is the minimum amount of energy required for a reaction to occur. It is always a positive value. Then, this option is incorrect. Option D says, the enthalpy change for the condensation of a gas to a liquid is a negative value. The enthalpy change of condensation is the amount of heat released when a substance turns from a gas to a liquid. It is always negative because heat is removed from the system. Think that when you want to do the opposite and evaporate a liquid, you heat the liquid. This statement is correct. The answer is D. In question 13, we have a Boltzmann distribution showing the activation energy for an uncatalyzed reaction. We are asked what is the difference for the catalyzed reaction and provided with 4 different answers. Using a catalyst lowers the activation energy needed for the reaction without changing the shape of the energy distribution curve. Essentially, it means the activation energy moves to the left. So, the answer is A. In question 14, we have that a student measures how the OH- concentration changes over time for a reaction and a plot is provided. We are asked what is the rate of reaction, in mole per cubic decimeter and second at 200 seconds. The rate of reaction is the speed of change of concentration of the OH- with time. We can measure it by drawing the tangent at 200 seconds and measure its slope. I get a value of -2.77 by 10 to the power of -4. The negative signs indicates that the concentration reduces over time. We take the absolute value and the answer is B. In question 15 we are asked which formula of the four provided does not represent 3-methyl but 1-ene. Drawing the structures helps in this type of problems. The 3-methyl but 1-ene is. In option A, if we draw the structure adding the relevant bonds, we have. That is 3-methyl but 1-ene. Option A is not the answer. In option B, if we draw the structure adding the relevant bonds, we have. That is also 3-methyl but 1-ene but drawn in the opposite direction. Option B is not the answer. In option C, if we draw the structural formula instead of the skeletal formula, we can identify it as 3-methyl but 1-ene. Option C is not the answer. In option D, if we draw the structural formula instead of the skeletal formula, this not 3-methyl but 1-ene, it is the 2-methyl but 1-ene. Therefore, the answer is D. In question 16 we are asked how many structural isomers have the molecular formula C4H9Cl. Structural isomers are compounds with the same molecular formula but different structural formulae. Drawing the structures will help in this problem. As the formula of the alkanase is CnH2n+1, we have a chloroalkane with a hydrogen replaced by a chlorine and with N equals to 4. So, we have 4 carbons that we will link together. Then, we insert one atom of chlorine and fill the chain with hydrogen atoms. We start with a linear chain of 4 carbons. We can insert the chlorine in the position 1, at any side of the chain, or in position 2, in any of the 2 carbons inside the chain. This gives us 2 possible isomers, 1 chlorobutane and 2 chlorobutane. The next structure is to use a tertiary carbon. In this structure, the chlorine can go to any of the primary carbons or to the tertiary carbon. This gives us another 2 possible structures, 1 chloro-2-methylpropane and 2 chloro-2-methylpropane. There are not other possible structures for C4H9Cl. Then, we have 4 structural isomers and the answer is C. In question 17 we are asked what is the organic product obtained when 3-methylcyclohexanol is reacted with sodium bromide and sulfuric acid. I leave a link in the fixed description where you can find a summary of the main synthetic reactions from OCR. The structure of the 3-methylcyclohexanol is. Note that it is not an aromatic compound. The reaction with sodium bromide in sulfuric acid will replace the OH group by bromine, giving as result 1-bromo-3-methylcyclohexane. Therefore the answer is A. In question 18, we are asked which compound could be the intermediate compound of a synthesis shown. We are provided with 4 possible options. As mentioned in the previous question, I leave a link in the fixed description where you can find a summary of the main synthetic reactions from OCR. For this question, we need to focus on what has changed between the reactant and the product. The double bond has been replaced by 2 hydroxyl groups. By quickly reviewing the options, we can see that with option D the synthesis can be achieved with 1 intermediate. The initial product reacts with bromine through electrophilic addition. Then, the bromines can be replaced with O groups using sodium hydroxide in a nucleophilic substitution reaction, yielding the desired product. The other options would be more challenging to obtain the final product with only 1 intermediate. Therefore, the answer is D. In question 19 we are given the infrared spectrum of an organic compound. We are asked to identify the compound that could have produced the given spectrum from 4 possible options. We start by identifying the peaks in the spectrum using the table from the data sheet provided in the exam. There is a peak at 3000 reciprocal per centimeter. This peak could be a carbon-hydrogen bond from alkyl groups, alkenes, and arones. There is a peak at 1700 reciprocal per centimeter. This peak could be due to a double carbon-oxygen bond. Any peak below 1500 reciprocal per centimeter is considered fingerprints. We now check the different options. Option A. There is no double carbon-oxygen double bond in the molecule. Additionally, the double carbon-carbon bond should give a peak in the region 1620 to 1680 reciprocal per centimeter, but the peak is not observed. We discard option A. Option B. There is no double carbon-oxygen double bond in the molecule. Additionally, the oxygen-hydrogen bond of the alcohol should give a peak in the region 3200 to 3600 reciprocal per centimeter, but the peak is not observed. We also discard option B. Option C, we have the carbon-oxygen double bond and carbon-hydrogen bond. Option C could give the spectrum observed. Option D. This molecule should show a broad peak in the region of 2500 to 3300 reciprocal per centimeter due to the oxygen-hydrogen bond of the carboxylic group, but this peak is not observed. Option D can be discarded. Then, the answer is C. Question 20 is about the structural isomers pentan 2OL and pentan 3OL with the molecular formula C5H12O and molecular mass equals to 88. The isomers can be distinguished from the fragment ions in their mass spectra. We are asked to identify the fragment ion which would be expected to be present in only one of these isomers. For this question, it is helpful to draw both structures and try to identify the fragments that would produce the different m/z values provided. There are different ways to reach the right answer. I will show here how I got it. It helps to know the m/z ratios expected for the sum of the possible fragments, that you can quickly calculate in the exam using the atomic masses. Starting with CH3 equals to 15, you can expand the chain with CH2 groups by adding 14 on each step. This gives you a guidance to deduct fragments. Option A, m/z equals to 29. This fragment is CH3CH2 and it is present in both isomers. A is not the answer. Option B, m/z equals to 45. Looking at the values m/z calculated and using the atomic masses of oxygen and hydrogen, we can identify it as CH3CH2OH. I know that it requires some practice. This fragment is only present in the pentan 2OL. Option B is the answer. For completion, I check the other two options. Option C, m/z equals to 59. As the molecular mass is 88, we can calculate that 88 minus 59 equals to 29, and as m/z equals to 29 is for CH3CH2, we remove this fragment from both isomers, leaving the following fragments. Option C is not the answer. Option D, m/z equals to 73. As the molecular mass is 88, we can calculate that 88 minus 73 equals to 15, and as m/z equals to 15 is for CH3, we remove this fragment from the isomers, leaving the following fragments. Option D is not the answer. The answer is B. We start section B with question 21. This question is about nitrogen trifluoride and boron trifluoride molecules. In part A, we have two questions. The first question is to define covalent bond. A covalent bond is a chemical bond that involves the sharing of pairs of electrons. The second question is to draw dot and cross diagrams of nitrogen trifluoride and boron trifluoride, showing outer electrons only. The answer is straightforward. Don't forget to put the lone pairs of electrons. In part B of question 21, we need to fill a table with the bond angles and the name of the shapes of nitrogen trifluoride and boron trifluoride and explain the differences between these two molecules. In nitrogen trifluoride, the nitrogen has 3 bonding pairs of electrons, each bonded to a fluorine atom, and 1 lone pair. The lone pair bond pair repulsion is stronger than the bond pair repulsion, causing the bonding pairs to be pushed closer together. This results in having a trigonal pyramidal shape with a bond angle of approximately 107 degrees. Boron trifluoride is an electron-deficient molecule because boron lacks of a complete octet. Its 3 valence electrons form covalent bonds with 3 fluorine atoms. The repulsion between the fluorine atoms causes them to spread out as much as possible, resulting in a trigonal planar structure with the angle around 120 degrees. The differences in the angle and the shape can be explained saying that boron trifluoride has 3 bonded pairs of electrons with 3 fluorine atoms. In contrast, nitrogen trifluoride has 3 bonded pairs of electrons with 3 fluorine atoms and 1 lone pair of electrons. The lone pair repels more strongly than the bonded pairs. Question 22 is about reactions involving acids. In Part A, we are asked what is meant by a strong acid. A strong acid is an acid that completely dissociate in solution. In Part B, we are asked to write equations for 2 reactions. The first reaction is the reaction of copper 2 oxide with dilute hydrochloric acid. This is a typical reaction where acids and metal oxides produce salt and water. In this case, the copper 2 oxide and dilute hydrochloric acid produce copper 2 chloride and water. The second reaction is the reaction of ammonium carbonate with dilute nitric acid. This is another typical reaction of acids, where they react with carbonates to produce salt, water, and carbon dioxide. In this case, we have that ammonium carbonate and dilute nitric acid produce ammonium nitrate, water, and carbon dioxide. In question 22, Part C, we have a student that carries out an investigation to identify an unknown group 1 metal M. We are given the details of the analysis and we have 4 questions. The student reacts 2.62 grams of M with water, forming a solution of the alkali, MOH. The student makes the solution up to 250.0 cubic centimeters with water. The student titrates 25.0 cubic centimeters of the solution with 0.165 molar of sulfuric acid. We are provided with the reaction of the titration. In the first question, we are asked to name the type of flask that the student should use to make up the 250.0 cubic centimeters solution of metal hydroxide. When we measure volumes with accuracy, the flasks used are volumetric flasks. Typically these type of flasks are indicated when the volume is given with 1 decimal place like 250.0 cubic centimeters. So the answers is volumetric flask. In question 2, we are asked to complete the table with the readings that the student takes to the nearest 0.05 cubic centimeters. The titer is the difference between the final titer and the initial titer, measured to 2 decimal places, as the readings are taken to 2 decimal places. These give the results of 20.25 for the first titer, 20.60 for the second and 20.35 for the third. In the third question, we are asked to calculate the mean titer of sulfuric acid, to the nearest 0.05 cubic centimeters, that the student should use to analyze the results. The first and third readings, 20.25 and 20.35 cubic centimeters respectively, are within 0.1 cubic centimeters difference and considered concordant. The second reading, 20.60 cubic centimeters, is more than 0.1 cubic centimeters difference, and therefore discarded. The average is calculated using the first and third readings, giving a result of 20.30 cubic centimeters. In question 4, we need to calculate the amount, in mole, of MOH in 25.0 cubic centimeters of solution and determine the identity of the metal M. With the concentration and the volume of sulfuric acid used, we can find that the number of moles of this acid is 3.3405 by 10 to the power of minus 3 moles. From the stoichiometry of the reaction, we know that 1 mole of sulfuric acid reacts with 2 moles of MOH, therefore, we have 6.70 by 10 to the power of minus 3 moles of MOH in 25.0 cubic centimeters of solution. As these 25.0 cubic centimeters were obtained from 250.0 cubic centimeters of solution, the initial number of moles were 6.70 by 10 to the power of minus 2. With the 2.62 grams of mass of M used and its number of moles, we can calculate its atomic mass as 39.1 grams per mole. And from the periodic table provided in the exam, we can identify M as potassium. Question 23 is about enthalpy changes. Part A is about reaction in petrol engines, and we have 3 questions. The first question asks to write the equation for the complete combustion of heptane. State symbols are not required. In a combustion reaction, the alkene reacts with oxygen to produce water and carbon dioxide or carbon monoxide, depending on the amount of oxygen present. In the case of complete combustion, we have that there is enough oxygen to form carbon dioxide. In the case of heptane, we have that 1 mole of heptane reacts with 11 of oxygen to produce 7 moles of carbon dioxide and 8 of water. In the second question, we are given the equation for the removal of carbon monoxide and nitrogen monoxide produced by the combustion of petrol engines. We are asked to complete the enthalpy profile diagram given. We are asked to label the enthalpy change of reaction, to include the formulae of the reactants and products, and to label the activation energy. The diagram is straightforward. As the reaction is exothermic, the enthalpy of the products is going to be lower than the enthalpy of the reactants. The difference between these two values is the enthalpy change of reaction, delta H. Do not use double-headed arrow on this enthalpy as it will reduce your mark. The activation energy is always a positive value. In the third question, we have that the carbon monoxide and nitrogen monoxide are removed by the use of a catalyst. We are asked to explain the role of the catalyst, referring to the enthalpy profile diagram. As the questions is awarded with 2 points, we need to mention 2 points in our answer. For example, 1. The catalyst lowers the activation energy. 2. The reaction proceeds via a different route. In part B of question 23, we have the reaction of iron oxide with carbon monoxide and the enthalpy changes of formation of iron oxide and carbon monoxide. We have 2 questions. In the first question, we are asked to state the conditions of temperature and pressure for standard enthalpy changes. We have to distinguish between standard enthalpy changes conditions and standard temperature and pressure conditions. They are closely related, but they are not the same. Standard enthalpy changes are defined under conditions of 298.15 Kelvin or 25 degrees Celsius and 100 kilopascal of pressure. Standard temperature and pressure, often used in gas calculations, are set at 273.15 Kelvin or 0 degrees Celsius and 100 kilopascal atmosphere of pressure. The answer for the temperature is 298.15 Kelvin. The mark scheme rounds this number to 298 Kelvin, or 25 degrees Celsius, and for the pressure is 100 kilopascal. The marking scheme allows values of 101 kilopascal, 1 atmosphere, or 1 bar. Before 1982 the accepted value was 1 atmosphere of pressure. In the second question, we are asked to calculate the standard enthalpy change of formation for carbon dioxide gas. The enthalpy of a chemical reaction is given by the difference between of the enthalpy of formation of products and the enthalpy of formation of the reactants. For the given equation, the enthalpy of the reaction, is going to be the results of adding 2 times the enthalpy of formation of the iron and 3 times the enthalpy of formation of the carbon dioxide, and subtract to this number the result of adding the enthalpy of formation of iron oxide with 3 times the enthalpy of the formation of carbon monoxide. Replacing the values given in the problem, bearing in mind that the enthalpy of formation of elements, like the iron, is 0, we get that minus 25 is equals to 0 plus 3 times the enthalpy of formation of the carbon dioxide minus, open brackets, 1 time minus 824 plus 3 times minus 111, close brackets. Playing with these numbers, I get that the standard enthalpy change of formation for carbon dioxide gas is minus 394 kilojoules per mole. In question 24 we have the reaction of equilibrium between sulfur dioxide and oxygen to form sulfur trioxide. There are 2 questions. In the first question we are asked why the given equilibrium is a homogeneous equilibrium. A homogeneous equilibrium in a chemical reaction is when all reactants and products are in the same phase. In this case, all are gases. In the second question, we are asked to explain how changing pressure, temperature, and using a catalyst affect the equilibrium yield of sulfur trioxide, using Le Chatelier's principle and other chemical concepts. Le Chatelier's principle can be worded as when the equilibrium of a system is disturbed by changing conditions such as temperature, pressure, or concentration, the system will adjust itself to counteract the disturbance and establish a new equilibrium. Effect of pressure: an increase in pressure will displace the equilibrium in the direction of less moles of gas, and the given equilibrium will displace to the right, increasing the yield of sulfur trioxide. Effect of temperature: as the reaction is exothermic, the change in enthalpy is negative, an increase in temperature will displace the equilibrium to the left, reducing the yield of sulfur trioxide. Effect of catalyst: a catalyst will have no effect on the equilibrium and in the yield of sulfur trioxide. In Part C, of question 24, a mixture of sulfur dioxide and oxygen is allowed to reach equilibrium at a constant temperature and the equilibrium concentrations are shown in a table. There are 2 questions. The first question asks to write the expression of the equilibrium constant for equilibrium 24.1 and calculate its numerical value, giving the answer to an appropriate number of significant figures and in standard form. The equilibrium constant is straightforward, and replacing the values given in the table, I obtain 79,365. To give the answer to an appropriate number of significant figures, we need to have a look to the format of the data provided. As the concentrations are given with 2 significant figures, we give the answer with 2 significant figures. Using the standard form, the answer is 7.9 by 10 to the power of 4. In the second question, we are asked to explain, in terms of equilibrium, why an excess of oxygen is used in the industry. As per Le Chatelier's principle from Part B of this question, an excess of oxygen will displace the equilibrium to the right, increasing the yield of sulfur trioxide. Question 25 is about hydrocarbons. We have 3 questions. In question A, we are given the boiling points of butane and pentane. We are asked to explain the difference in boiling points between these 2 compounds. We can see that the butane has lower boiling point than pentane. The difference in boiling points can be explained by their molecular structures and intermolecular forces. Pentane has a larger molecular size and greater molecular weight compared to butane. Larger molecules generally have higher boiling points because they have more atoms and, hence, more surface area, which leads to stronger London dispersion forces. Both butane and pentane are nonpolar hydrocarbons, so the primary intermolecular forces acting between their molecules are London dispersion forces. These forces increase with the molecular size and weight. In part B of question 25, butane reacts with bromine by radical substitution to form a mixture of organic products. The reaction needs ultraviolet radiation for the initiation stage. We are asked to write equations for the propagation stage that follows to form 2-bromobutane. We need to use skeletal formulae and dots to show the position of any radicals. From the three stages of the radical substitution, initiation, propagation, and termination, we are asked about the propagation stage. Therefore, at least one of the reactants will be a radical and at least one of the products will also be a radical. As reactant we have butane, its skeletal formula is. The skeletal formula of the 2-bromobutane is. In the initiation stage, the bromine is going to form bromine radicals with the UV light. We start with the skeletal formula of the butane and the radical of bromine. As products, we put the radical in the position 2 of the butane and the hydrogen in this position reacts with the bromine radical to form hydrogen bromide. In the next reaction, we need to generate a radical, as it is a propagation reaction, not a termination reaction, and 2-bromobutane. We can use bromine to react with the radical of the butane and produce a bromine radical. In part C, of question 25, we are given a flowchart with 3 reactions of organic synthesis. We are asked to complete the flowchart to show the missing reagents, catalysts, and the structures of organic products. In the description of this video, I leave a link with the summary of the reactions pathways from OCR. Most reactions involving alkenes are addition reactions. During these reactions, one of the 2 bonds in the carbon-carbon double bond is broken, and each of the 2 carbon atoms form a bond. The reaction of the alkene to produce an alkane is via addition of hydrogen to the double bond using catalysts such as nickel, palladium, or platinum as a catalyst. The addition of hydrogen bromide produce the bromide alkane. Due to the symmetry of the molecule, we have only one product and Markovnikov's rule does not apply. We finally have the formation of an alcohol from the alkene. This is done via steam. If you put water, indicate that it is water gas, otherwise you might lose marks. With the presence of acid, typically phosphoric acid, but sulfuric acid or simply H+ are allowed in the marking scheme. As in the case of hydrogen bromide, due to the symmetry of the molecule, we have only one product and Markovnikov's rule does not apply. Question 26 is about the oxidation of 2 alcohols that are structural isomers of with formula C3H8O. We are asked to compare the oxidation of these 2 structural isomers using different reaction conditions. For each reaction, we need to include the reaction conditions, the functional group of any organic product and balanced equations, using capital O with square brackets to represent the oxidizing agent and showing any organic compounds as structures. In the description of this video, I leave a link with the summary of the reactions pathways from OCR. The formula indicates that the structural isomers are saturated alcohols with 3 carbons. We have 2 possible options, 1-propanol and 2-propanol. The oxidation of the alcohol depends whether it is a primary alcohol or a secondary alcohol. In primary alcohols, we can get aldehydes if we separate the products by distillation, carboxylic acids if we heat under reflux. In secondary alcohols, we get ketones under reflux. Tertiary alcohols do not oxidize. In all cases, we get water as a subproduct, easy to forget in the exam and lose marks. Oxidants are typically acidified potassium dichromate and acidified potassium manganate, however, the question does not ask for these. In the case of 1-propanol, we have a primary alcohol. Depending on the conditions, we can produce an aldehyde using distillation or a carboxylic acid using reflux. In the case of 2-propanol, we have a secondary alcohol, that will be oxidized under reflux to a ketone, with no further oxidation possible. And this is the end of the paper. If you want to see more videos like this, please click like, and leave a comment, as it will help me to carry on making more videos.